Yes, sir.
So I
Yes, sir.
think this is where we had stopped day before yesterday. Today is the sixth class, post semester session, CH425 and CH812. Welcome. Now this is exactly what I had, the first order correction to the wave function. So idea is as follows: the first order correction to the wave function is a linear combination of all the zero order eigenfunctions, isn't it? N stands for the nth state, the nth eigenstate. So this is a first order correction to the nth eigenstate. Okay, and this is exactly what I received, because you have to multiply with lambda in order to get the amount of change. So we will start from here. Okay, so let us start. Uh, let us begin by, okay, okay. Can everyone see? Can you see the screen? Big enough?
Yes, yes, sir. Yes, sir.
Okay. So the idea is as follows, that you start from here. So now, can you tell me what is the correction? What is the correction to the wave
For the wave
function?
function.
Yes. Without looking at your class notes, can you tell me what it should be? So let me write it down.
Uh,
So lambda psi n equals to
So let me write only psi n, psi n 1.
psi n.
Now this
Yeah,
is clear. This is n for the nth eigenstate, nth state
first order.
or level, and this is first order. This should be clear to all of you. Okay. So if I write psi n 2, what does it mean?
Second order nth state.
Second order. You can try find out what is the second order correction. Try to find out. I am not going to do it. But anyway, let me write down the first order correction again. Obviously, you know this is going to be a sum over. Let me write down. It is sum over something like m or l, whatever you want. This is the idea. This one you can write. For that, you don't need to remember anything, no? All of you. For this, you don't need to remember anything, no? The one I had just written here.
Yes, sir.
Because this is from basic quantum mechanics. You may not remember what is the expression for CL. That is the problem, no? That you don't remember. Difficult to remember, I know. So I'll write down. This is exactly I derived. L0 to infinity. We don't have L. L is not equal to N. I'll come back to that later. And you had something like, you remember what you had? You had an integral of, you remember, because you had this psi L star 0, then H1, what you had here, psi n 0. You remember this? See, look at it. It is not very difficult. Now it is not very difficult. Just look at it. Not very difficult, no? To remember.
Yes, sir.
I can just write it. You can simplify it further using some notation. What is this? This integral I had written. This is a nothing but a matrix element of H1, but L n. Remember? Divided by this. This is fine with you. This is 1. Okay? This is fine with you? To all of you.
Yes,
Tell me.
yes, sir.
M to psi L0.
Yeah. That I have not written. Yes. So there is H 1 L N psi L 0. Very difficult to write using stylus, at least for me. So this is fine. This is very neat. This is very neat. Now, why I said there is no L equal to N term in that sum?
The term Cn will be 0, 0.
It is not like that. It is because
Sir, it will.
you can include, but it will
Sir,
take care. It will be taken care when you integrate. Sorry, you normalize the function, isn't it? Ideally, you should also have like Cn, psi n, but you have psi n on the left hand side, isn't it? You have psi n on the left hand side. What is the point of writing another psi n on the right hand side, isn't it? That's why you don't write. Is it okay? Because that will be taken care when you normalize this wave function. When you normalize this, that will be taken care. Okay? This is clear to you. Is it clear?
yes, sir.
This is very simple. There is nothing big about it. Now, I will recall one equation, because if you go back, can you see? We have done this. Now we had this, no, lambda square, the coefficient of lambda square. You had 5 terms there. 1, 2, 3, 4, 5, all these terms. Huh? Okay. Now we'll
Yes, sir.
concentrate on this because I want to calculate what is known as second order correction to energy. Then I should have to start from here, no? If I want to know what is the second order correction to energy, I should go and look into this equation, isn't it? Are you convinced that I should go there, here, and look into this? Because this lambda square means the second order, no? Lambda to the power 1 means first order. Lambda to the power 0 means zero order, which is unperturbed, exactly solvable model. Now this is this equation. I'm going to write it again. Now, even if you don't remember, you can write it, isn't it? What is the rule? The rule is as follows. You remember the rule? What is the rule?
The sum should be equal to 2 for second
Yes,
order,
yes,
the
yes.
above power.
And all the expression with En, they will come with minus sign. See, all the Ens are coming with minus sign, isn't it? Because it is on the right hand side. When you take them to the left hand side, it will appear with minus sign, isn't it?
Yes, sir.
So you don't need to even derive this. You can just write it down. So if I write it down, there will be 5 terms. Okay. Remember that in the Hamiltonian you have only H0 and H1. So then first term will be H0 psi n2, then you will have H1 psi n1, and then you have 3 terms with En, En0, En1, En2, and accordingly you will have psi part there. If it is En0, then you will have psi n2. If it is En1, you will have psi n1. If it is En2, then you will have psi n0. Is it okay? Should be fine.
Yes,
Yes,
sir.
yes,
So
sir.
let us do
Yes,
it.
sir, it's fine.
So now you got how to do it, the trick, how to remember. Okay, so let us write it down. So what is the first term? So what I'm going to do, I am going to do second order correction to energy, no? Second order correction to energy. Okay, so we go back to that equation, write down what is the first term? H0 with psi n
Psi n2.
2. Next one is H1 with psi n,
1.
then minus En, say En 0, then it is
Psi n2.
Psi n2.
En1, then
Psi n1.
psi n1. Okay, and then I can take this thing on the other side. Let us take it En2. This is fine. This is the equation you had, no? essentially. Now multiply the whole equation with psi n, multiply with psi n 0 star and integrate. If I do this, what is the first term I'm going to get? I can actually, I'll just separate psi n2, psi n1, these two terms separately. So I'll take first and the third term together. So what I'm going to get psi n 0 star. Look at carefully. H1. So I have taken psi n2. Psi n2 is here. Sorry, not H1. This is a size H0. En0 this is fine. This term and this term. What is the next
Yes.
term? Plus integration. Okay, d tau I am putting it here. The better looking. Better to put it here. Doesn't mean much, but anyways. What is the term? Tell me. It is very difficult to write on if it is not blackboard. The first term is
Psi n1, psi n0 star.
psi n0 star. Sometimes actually the star should be after 0, but doesn't matter. I'm not very particular. This one, then this term, no?
H
No, this one, H1, no?
H1.
And
Yeah.
this one is E1. So it will be like and on the right hand side, what I'm going to get? This En is a number, so I can take it outside the integral. And I'm going to get what is this integral? Can anyone tell me?
1.
It is 1. It is normalized. What about this integral? The first one. Can anyone tell me what is the value? The first one.
0.
It will be because it's Hermitian, no? Because this will also can operate on the left. It will give you En0 star, which is En, of course. So this will cancel. This will also give you 0. So what I have left with? I have left with En2. And En2 is equal to this integral. What is that integral? So let me write down again. D tau psi n0 star with H1 and En1. Sorry for the bad handwriting.
Sir,
Oh, that is N, of course. Yes, tell me.
sir, can you please explain the 0 part?
Yes. Yeah, because this is Hermitian operator, no H0, Hamiltonian. This is a
Yes, sir.
Hermitian operator. So I just use the Hermitian property. If it is Hermitian operator, what will happen? It can also operate on your left, no? So if I split this, I'll have two integrals, no? The first one is psi n0, h0, psi n2 minus en0, psi n0 star, psi n2. And the first term is exactly the same as, you remember that.
Oh,
if I
okay.
split this,
So
yeah,
psi
just
0 will operate
yeah,
on H0. It will give me En0
yeah, n0. So
and psi
n0,
0
n0
as it
cancel.
is. Yeah.
N0,
Okay,
n0
sir.
will carry. Yeah. So
Okay, sir.
essentially, I'm just keeping one step. Huh? I'm writing to so many steps. So now I have the expression for En2. Okay, is this fine? Now what is left? What is left? En2 is there. Then what should I do? I should do this. Because here, what is this? This one is given by what? Remember? Something like that, isn't it?
Yes, sir.
You want L, you want M, or these are dummy variables, so it doesn't matter. You can also write M. Okay. Okay. This is your EN2. Is this fine? Whatever you
Yes,
want,
sir.
right? EL,
Yes,
L
sir.
or M. So now I go back. So I just replace this expression. So my expression is now going to be EN2 is given by d tau, because I had multiplied this with psi n 0 star, and you had this H1 minus En1. Sorry for this. And then I can write, you know that it runs for all the values of. This is exactly what you have, isn't it? Is it fine?
Yes, sir.
Now this one, I can exchange the order of integration and the sum. Sum, I'll take it here. I can do the sum later, doesn't matter. So what will be the first term? D tau psi n 0 star. Can anyone tell me what will be the first term? H1 psi n 0. This is fine. And what is the next term?
En.
Let me do it first. Cm, and then you had this En, and then the integral. But you can put this, or if you want, En1, you put it here, and do the integral. Integral is
Psi n0 star psi m0.
okay. This is fine, I think, because my handwriting could be bad, but more or less you understand what I have written here, isn't it? What about this guy? The second term. Somebody already said what is the value.
0.
This is 0. So then what I have left with? I have left with only one integral. One integral.
Yes, sir.
And can I use a shorthand notation for this? If I use a shorthand notation for this, what will be the shorthand notation? It will be the matrix element for H1, no? Nm, isn't it?
Yes, sir.
This is fine. So now I have an expression, very neat expression for your En2. So your En2 is going to be net expression for En2. En2 is going to be
Summation
over
Cm.
Cm H Nm H1 Nm. Okay. Now you know there is an expression for Cm, no? So if I replace that, this is equal to what? It is actually M02 if I write explicitly. But there will be minus term coming, no? Because Cm had this minus term. And you remember the expression for Cm? It is here. This one. Cm has to be, like, if I am using M, it should be M. Hmn minus, divided by this and minus sign, isn't it? So it will be minus Hmn1 divided by, tell me, Em0 minus
En0.
N0. This is for the Cm part, and then I have this H1 and M. This is fine. H1 is also Hermitian. How does it help? How does it help? It is Hermitian. It helps because I can further simplify this. It basically means that Hmn is equal to H like this, no? 1. Sorry, huh? This is, you understand what I'm saying? So what is going to happen to this? So next term would be minus, you took it out, whatever is there, it will be H nm star, of course, 1 star H1 nm divided by em0 minus em0. Next you have this. Of course, so it basically tells you it is minus H nm1. This is fine if I write like this. I hope
Yes, sir.
you can follow. Absolute value. Okay, then what will be the lambda square En2? This is the second order correction to energy, no? What is this? This will be lambda square will go inside, isn't it? So it will be like lambda H nm1. This is the absolute value square. Minus is there. Sum. It is inside the sum. Okay? Is this fine?
Yes, sir.
Now what about em0 minus en0? Now this term is always positive. The absolute value square is always positive. Let me write down like this. Always positive, Noida? This one? This one is positive, no, always positive. What about this guy?
Negative.
No, em0 minus en0. Is it negative or positive? How do you know?
It can be anything, positive, negative, or zero maybe. No, not zero.
No, it is not 0 because m is not equal to n. Let me write down here. So you don't know, isn't it?
Yes, sir.
Non-zero, that is you know. Okay, but if one want to see this quantity, lambda square E02, second order correction to the energy for the ground state. For the ground state. Tell me what is going to happen. This one is going to be whatever, I'm not writing, but for this you need to find this em0 divided by E00. This is positive or negative, this one. You had this, no? When n equal to 0, you'll have this. Now what is this quantity? Is it positive or negative?
It is positive, I think.
It is always positive because m is above, because ground state is the lowest energy state, no? And m is not equal to 0. So basically m is anything above 0. So by definition, if I assume, okay, the definition is such that this is, as you go up, your energy increases. This is positive. What does it mean then? It basically means what? What will be the Sign for this. What is the sign for this? Can anyone tell me?
Negative.
It is negative because positive divided by
Negative.
positive. But then you should not forget there's a -1 sitting there. No. This is negative. This is quite nice. So the second order correction, let me repeat. The second order correction to energy for the ground state is always negative. Am I clear? Second order correction to the ground state, energy is negative. Does it ring any bell? Anything? Does it ring any bell?
So the energy will be like lower compared to what is
Yes,
expected.
without perturbation. Without perturbation. Yes. So can you give me an example?
As if you showed in like particle in a box, like that was
Yes,
something
that
like
you
that.
can calculate, but more realistic example I'm not going to do because very lengthy derivation.
Staff effect.
Yes,
SHO, sir.
but yes, yeah, all these things you know, but I'll give you even more fundamental. So when you talk about say two molecules or two atoms interacting, you know there is something called van der Waals interaction. How many of you know van der Waals interaction?
Yes, sir. You know.
Yes.
So what is the functional form for the van der Waals interaction? It is attractive. You remember this is attractive. This is
Leonard potential.
yes. So if you take Leonard-Jones potential, it has one attractive term, one repulsive term. The attractive term I'm talking about, it is -1 over r to the power 6. You remember? How many of you remember?
Yes, sir.
Sir.
Yes,
So
sir.
that comes because that is the second order correction to the ground state energy. Because of that, it is negative. The origin is quantum mechanical. So actually, you can do a calculation. You can take two hydrogen atom, for example, and do this calculation and show that the van der Waals interaction is something like small r. This negative sign comes because is a correction, second order correction to, and you see if you do this calculation for hydrogen atom, the first order correction is 0. There is no first order correction. So the lowest non-zero correction comes from this second order correction, and that is minus of 1 over r6. Now can anyone tell me, this is not related to this course, but why it is r to the power 6? Physically, why? I'm not going to do the math. It is too lengthy for this course. I can set an assignment problem on this, but I'm not going to do it here. Can anyone tell me why it is
Very big force.
no, why it is r to the power 6?
So something like interaction between instantaneous dipoles.
It is like that. So you have actually an instantaneous dipole created on one hydrogen atom, say, because you have nucleus and electron. One dipole, another dipole, and this dipole-dipole interaction, you know, from your electrodynamics, it's 1 over r cube. How many of you remember? Dipolar interaction is 1 over r cube.
Yes, sir.
Yes, sir.
And what you have here, you have some matrix element square. So if one matrix element gives you 1 over r cube, what is 1 over r cube square?
1 over r to the 6.
Yeah, so that is the origin. Did you know this? I think maybe Anish, few people would know, but not everyone. Did you ever realize this? And this is the standard potential used in classical MD simulation, for example. They use this kind of interaction, van der Waals. So this is the attractive part of van der Waals interaction. Sorry, Leonard-Jones potential.
Sir, I have a
Yes.
doubt. So if we are considering two system and both are in same energy state, then n is going to equal to m, and then energy correction will be infinity. Then how to define that?
We have already said that the n is not equal to m, no, throughout our derivation. Don't look at this expression. see how this expression is derived. When you are derived, you are assume that m equal to non. So this expression is not valid for m equal to n.
Okay.
You cannot put m equal to n here. How can you put?
No, but sir, we are talking about two different particles that is in same state. So
No,
is
no,
it?
no, no, no. We are not talking about we have only one particle. There is no two different particles here.
Then okay. Thank you.
No, there is no two particle in such. So please go through my notes and my videos again and again and read some books.
Okay, sir.
So Anish and others, is it clear? That physically why it is 1 by r to the power 6 with a minus sign. So in classical MD simulation, whenever you do, all these potentials are actually the origin is quantum mechanical. Is it clear to all of you?
Yes, sir.
So this is like 1 over r to the power 6. So we'll not discuss this. But I'll give you one example. So for example, if I take polyene, linear polyene, and I put it vertically. This is a weird thought experiment. This is R vertically. So this is how you put the molecule. Okay, this is Z is the direction, Z0, and this is some Z equal to A. You remember that we map this onto 1D box problem. Then what is the potential, this V prime perturbation? What is the perturbation in this case? Now perturbation is because of is due to gravitational field. What will be the perturbation if it is due to gravitational field? Essentially, you put the molecule like this, okay, on the ground. The height of the molecule is like the length of the molecule is A. Then what is the perturbation acting on the electron along this direction?
MGZ.
Of course, you know that it is nothing but V prime is going to be mg h. H is in the z direction, so this is fine. This is from your school physics. Okay. Now let us calculate, for example, first order correction to energy. So the ground state. Ground state is 1. This is the first order correction to energy. First order correction. Of course, you have to multiply with lambda, but okay. G for the ground state. What is the formula? How many of you remember?
Size 00 H1 into size 00.
Yeah. Not 0, it is psi 1, no?
Psi 1, yes, sir.
H1 is this, whatever. This. So the H1 is going to be, okay, let us put it H1. It is D Z 0 to A. Now what is psi 1?
Sir, it will come out to be really like negligible, I think.
yeah, of course. That is the whole point.
Yeah, the mass of electron is 10 to the power minus
Yeah, yeah.
31, so it will
Yes,
be
yes.
like
Okay, yeah.
not of
So now
any
if I do
importance.
this, you know this. Essentially your H1 is Z. This is like mg times what? Average value of Z, isn't it? What is average value of Z for particular box in the ground state? This is mg
A by 2.
Z by
yeah,
2. Z by 2.
mg A by 2. And you put it, this is negligibly small if you put the values. But with the assumption that you are on Earth. On Earth. If you go to neutron star, what will happen?
the value of G will increase like really.
Yeah. This is just a simple thing because then the value of G, acceleration due to gravity, is different on neutron star. If you go there, isn't it? Okay?
Yeah, some similar thing will happen in black hole too.
Yes. Yeah. So that physicists, they are interested. We are not. But now we'll stop here. But one thing you must have realized that second order correction is lambda square and lambda is tiny. So as I move on, higher order corrections are smaller, sometimes smaller, depending on the system. But usually it should be like we'll do. There are cases also we'll do later. But one thing I'm going to do here, I'm going to discuss what is known as variational method or variation method. How many of you heard about it, variation method? Some of you had, I am sure. How many?
I
Yes, I
just
just
wanted to
heard,
make
but
an
don't know
observation from the
anything.
previous part. If you know,
What?
so this whole method would not work for degenerate cases, as is pointed
Yeah,
out.
yeah, we did not
That
discuss.
yeah.
It will not. It will not. It will fail. Completely fail. You are right. I just did not discuss because we had assumed that you have a system which is which has no degeneracy. Okay. We just discuss non-degenerate perturbation theory. So there is another formalism when you have a state which is degenerate, then this formalism will not hold. Okay. But we are not going to discuss because I don't think we have time, because we have to do this valence bond theory, molecular orbital theory, and other things. Yes, someone has a question. Someone has a question. Okay, so now we will introduce what is known as variation method. Now this is a very important because in all the packages people use, you will know, some of you would know, there are computer like quantum mechanical or quantum chemical packages or software. Uh, they are used to calculate the energy levels of molecules. There are packages like Gaussian. You have heard Gaussian or
Yes, sir.
MolPro and others.
Yes, sir.
I think all these packages, they make use of this variation method, what I'm going to discuss now. Of course, briefly. And we'll see what does it mean. So let us start with helium atom. Helium atom is not exactly solvable, you know that. You have one electron, sorry, one nucleus, two electron. Okay, so this distance is R1, this is R2, this is R12. Electron 1, electron 2, this is your nucleus which has charge Z times E. Then what is the Hamiltonian? Of course, minus h cos square by twice m. Electron mass of the electron is m. What does it mean, this partial derivative with respect to
Laplacian.
1? A Laplacian, what is that? This is
Del 2 del x2 plus del
yeah,
2.
derivative with respect to what?
Cartesian coordinates.
To the
X, Y, and Z.
coordinate of the first electron, no? One means first electron, no? Similarly, you will have another term. This is for the second electron. What else? You will have interaction, attraction between electron 1 and electron 1 and the nucleus. This will be Z square with a minus sign by 4 pi epsilon 0 R1. What is the next term? Z square 4 pi epsilon 0 into R2, and then there will be electron repulsion, no? And
Yes,
that
sir.
is ZE.
So Z will not come.
Yeah. So it is E square. Okay. E square, but with a positive sign. 4 pi epsilon 0 into R1, 2. This is, I think everybody knows this, isn't it? And if you have an integral variable like this, z tau, in this case would be dr1, d theta 1, d phi 1 into dr2, d theta 2 into d phi 2. Or it is equivalent to say dx1, dx, dy2, dz2, dx2, sorry, this is 1, 1. Okay, just you know all these things. Now in this case, the Hamiltonian is given by this. So, and you have this equation, eigenvalue equation, but this is not exactly solvable, no, for helium atom. Okay, is this clear that it is not exactly solvable for helium atom?
Yes, sir.
Yes, sir.
So this energy E is given by psi star h psi e tau divided by psi star psi. This is the exact expression. This is nice, expression is nice, but useless. Why useless? As we don't know psi, no? Because you cannot solve h psi equal to e psi exactly. Okay, are you convinced that this is nice expression but completely useless if you look carefully? Why? Because I don't know psi. If I don't know psi, how can I calculate energy? In order to know psi, I have to solve h psi equal to e psi, this equation, time independent Schrodinger equation. But I cannot solve in this case for helium atom. Why? Because of this electron repulsion. You will have tried to solve analytically, they could not solve. There are people who are still working on it. You can solve it on a computer, but let us do something else. Can we guess a solution? So let us guess a solution. Say this is phi. Okay, your guess solution. So guess wave function. This is called guess wave function. I guess it. Okay, this is something which I guess, and then I calculate this quantity phi star h phi d tau phi star phi d tau, and this one I'm calling it something like this one. This is called script E.
Sir.
Okay, and this is obviously let me finish. This is some approximate energy. This is not equal to E. Yes, someone has a question. Yeah.
Yes, sir. Here, basically, what we are writing is the expression for average value of energy, right?
Yes.
Okay, okay,
Nothing else. The expectation value.
okay.
I think it is taught, isn't it?
Yes,
This is
sir.
one
Yes,
of
sir.
the postulates. Yeah.
Yeah.
So now if I am doing this for the ground state, okay, this the ground state energy is E naught, Boundary energy is E naught. It is possible to show that whatever gas wave function you take, and calculate the energy, this is going to be equal to greater than equal to E naught, and this is called variation principle. Variation principle. We'll work on it and prove it in the next class. Okay. So for example, if you guess one wave function, phi guess 1, that gives you energy say for hydrogen atom, I'm doing say hydrogen atom. I know the exact solution, but I guess something and then I do this energy calculation and I get this to be minus 10 electron volt. And phi guess 2. So guess 2 is something which you have guessed. You also calculate this energy, you guess 2, and this is minus 12.6 electron volt. Which one? You know that E exact, E naught is what? 13 point, how much?
6.
13.6.
6.
So which one is better? E guess,
Guess 2.
phi guess 1. This is better. Better guess,
Guess.
isn't it? Okay. So now let us, we'll come to that variation principle later. So let us concentrate on our problem, or the most popular model system, particle in a box. Particle. Particle in a box. So what is the energy for the ground state? I remember pi square h cos s square twice m a square. This is the ground state energy. This is discussed, I'm sure. This is h square, you know, this is the expression, you can go and check. This is perfect.
Yes, sir. Yes, sir.
So let us guess an wave function. We know the exact wave function, of course, the sine function, but let us guess. And our guess is like this, phi, which is x into a minus x. This is not a bad guess, no? Of course, when you are within the box, this is fine, because when x is equal to 0, what is the value? 0.
0.
And x is equal to a, again 0. In between you have some value, no? It is ax minus x square, you know. So this will have, how does it look like? How does it look like if I plot it?
At first, it will increase and then it should decrease.
Increase and then decrease. It looks something like this. You can check, go and check. Okay. So the simplest one, very simplest guess. Which one? Simplest one which follows the boundary conditions. Okay. So let us calculate the E script. What is the expression? 0 to a expectation value. Remember, 0 to a. What should I write? Tell me.
X into a minus x.
Then
Hamiltonian and then this again.
And you know the Hamiltonian for the particular box inside the box is this. And what is in the denominator? X into a minus x. Again,
Square.
this is what it is, isn't it? Essentially,
Yes.
this is. So let us do this, the first one, the first integral, the numerator. Let us do it. So what it is going to be? This is ax minus x square. What about this? This is a constant. If I take a second derivative of this, what I'm going to get? Let us do it.
-2.
This will give you -2. Huh? Okay?
Yes, sir.
So I can
Yes.
put it here. So if you take it outside, I'm going to get the first term is going to be ax dx minus this, fine.
Yes, sir.
So let us do it. This will be a, this is going to be x square by 2. So let me do this. This one is x cube by 3. What you're going to get? This is, tell me, this is,
A cube by 6.
yes. No, this is fine. This is going to be a cube by 2 minus a cube by 3, isn't it? This is fine.
Yes.
What will the answer? A cube, this is 3 minus, it is a cube by 6. This is fine. This is expression, no? Is this fine?
Yes, sir.
What about the denominator? It is 0 to a. Actually, what you have here is x square into a minus x whole square dx, which will have many terms. The first term is going to be 0 to a. Let me do it. A square minus 2x plus x square dx. Sorry, I know it is boring for some of you. The first term will give you s square. X square dx is x cube by 3, 0 to a, minus 2a. This x cube dx will give you
X raised
x
to power
square
4 by 4.
4, 0 to a, and then plus x to the power of 5 by 5, 0 to a, isn't it? Is this fine?
Yes, sir.
I hope I have not done anything wrong. So I am taking it there. So what is this now? The first term will give you what?
A raised to power 5 by 3
Next one will give you
minus 2 A raised
2
to power
and
5 by 4
but 2 by 4 you can calculate just x square 5
by 2.
by 2 plus by 5. Fine.
Yes, sir.
And then what is the answer? Sorry. 10 minus
A
15
5
plus.
A raised to power 5 by 30.
So actually, if you add this, you will see what is going to happen. A to the power of, so this is 5. Huh? So what does it give? The scripted E. The scripted E, if you calculate, you're going to get H cross square by M 6M. It is like that, no? It is actually, I'll write like this: H cross square by twice M into A cube by 3 divided by A to the power of 5
5.
by 30,
30.
isn't it?
Yes, sir.
So what is the answer? H cross A square by, say, twice M A square. This is fine. Into what factor? Factor of 10, I think, no? Just check. Is it correct or not? Just check.
Yes, sir.
Yes, sir.
And now what was E1, the ground state energy? I had written here. It was H cross A square. Okay. Now what is the value of pi square?
So
9.
9.9 something.
Okay, someone has a calculator. Can you calculate and tell me the exact value? The closest possible value, not exact.
9.87.
9.869. 86.
86. 9.86.
Okay. So E is greater than E1. The ground state, of course. Huh? What is the percentage? Can anyone calculate? How much? You can just calculate the percentage error.
1.3%.
1.3%. It is very, very small. So this is quite nice actually. If you have a Gauss wave function, then it will give you energy which is slightly above the ground state energy. E naught, in this case, E naught is E1, of course, because the lowest possible energy is for n equal to 1. So it is very close, but it is slightly above, just 1 point some percent, 1.3%. Is it clear to all of you? I
Yes.
hope it is clear. Okay. So now, at least, now in the next class, I'm not going to continue today, because if I start today, I don't think it's a good idea to start. I'll give you some time to read books and my class notes and go through my videos. So we'll conclude a little early today. But so far, so good. I hope that you could follow whatever being taught till today. I'll just recap. I can recap this. Okay. So I'll start from the previous class, and whatever I have today, I'll recap. And so let's start here. So in the last class, we started with this perturbation theory in quantum mechanics. Why do we need this? When I recap, you should also answer. Why do I need perturbation theory? What is the need? Any other, this is an approximate method to calculate. Why do I need this?
Problems that are not exactly solvable.
Because most of the problems are not exactly solvable. You need to know, do it on a computer, or need to have some approximate method. So one method is perturbation theory. So H psi equal to E psi is not solvable for many systems, like helium atom, for example. So even if you take a particular box like with a small perturbation like this, it is difficult. So then you have to make use of this theory, perturbation theory, and it is based on the assumption that the change in the Hamiltonian is negligibly small compared to the total Hamiltonian. A small change in the Hamiltonian. And you had this. So your total Hamiltonian, which depends on some parameter lambda, is given by H0, which is Hamiltonian for the unperturbed system, for which the Schrodinger equation, time independent Schrodinger equation, can be solved exactly, plus a small correction due to perturbation, lambda times h1. So you have all set of eigenfunctions with h naught. They are going to change when you have this perturbation on. I don't know what are the solution. So I just expand your eigenvalues and series in lambda so as the wave functions in series of lambda. And I want to solve this h psi n equal to e n psi n equation. And I just expand this and then match the coefficient of lambda square, lambda 1, lambda to the power 2, and the lambda to the power 0. Sorry, lambda to the power 0 coefficient would give you the unperturbed Hamiltonian equation for the unperturbed Hamiltonian, which is your time independent Schrodinger equation. And then you have lambda 1 and lambda to the power 2. For this you have other set of equations. And now you know the trick how to remember this, no? All of you? So what will be the terms?
Yes, sir. Total sum will be lambda to the power.
What about the coefficient of lambda? Okay. Here I assume the lambda has integer coefficients. Okay. So and then we did some little bit of algebra and whatever, and you showed that the first order correction to energy is given by this. It's very simple. The perturbation sandwich between the grounds, between the zero order wave function, or the nth. N stand for the nth level or nth state. Okay. And also we did we did some calculation for particle box problem, and also we calculated the first order correction to the wave function. That you are done, isn't it? And this is given by, the idea is as follows: the first order correction to wave function is a linear combination of zero order wave functions, because this wave function also is also in the same Hilbert space. So you can actually express this wave function in terms of other wave function. Okay. And actually if you multiply this with psi m0 from the left hand side, and psi l0, you'll see that all the terms will cancel, only one term will survive. What is that? On the right hand side, this is psi l star 0 and psi l. So that will actually give you the value of the coefficient, and you can normalize the wave function. Is this clear? You can take this, multiply it with say psi l0 star, then you will have psi l0 star inside, and you'll have many such terms. Psi l only when l equal to m, that will survive, isn't it? I can do that. But what will happen that if l is not equal to m, that will blow up. So that will give you the coefficient of L, psi L. Anyway, we had calculated the coefficient CL and is given by this expression, and that will give you the first order correction to the wave function. And this is where we stopped in the last class. And today we have done, let us do it, recap today's thing. Today we have done this, the first order correction to the wave function. We just wrote down the expression again, and then we looked at second order correction to energy. And I showed that this is given by this expression shown here, and this is negative if you are considering the ground state correction to the correction to the ground state, second order correction to the ground state energy. It is negative. One example is your van der Waals interaction between atoms or molecules. This is negative. And then we introduce variation principle or variation method, and we have not proved the variation principle, which we will do in the next class, but we showed that for the particle box problem, one can guess a wave function and calculate the energy, and this energy is going to be slightly above the zero. Not zero means the ground state, in this case n equal to 1 energy. And you stop here today. So I suggest you to go through some book. Okay, so one good book to go through would be, there's a let me write it down here. I don't know how many of you know this book. This is called Molecular Quantum Mechanics by Atkins and Friedman. molecular okay. This book you can have a look. It has a good discussion on, or any other book. You can even look at Levine, Quantum Chemistry by Levine. That should be fine as well.
Hello, sir.
Yes.
Hello.
Yes. Tell me.
Sir, you have said that for the van der Waals interaction, the interaction is due to mainly dipolar interaction. So that is proportional to the 1 upon r cube, and then the matrix element gives the square of that. That is minus negative of 1
Minus
upon r to
sign
the
is
power
there,
6.
no? Yeah.
And sir, yes, sir. Yes,
Yes.
sir. And sir, we know that Leonard-Jones potential, that is often called the 612 potential.
12 comes
Right,
from
sir?
the repulsion part. So I'm talking about the attraction.
Yes, sir, that's fine. But I am asking that where the 12 term comes from. There is another thing.
I understand. So 12 term comes because when you bring these two hydrogen atom together, close to each other, 12 term comes when they're very close. What will happen that this electron will start feeling the repulsion from the other electron. The other one, the one I talked about, it is at the large length scale. Large length scale, okay? When they're separated by a large distance. Not very close. When
Okay.
not very large at the same time, some intermediate length scale, intermediate distance. And now when they're in the, what happened that at this length scale, this electron will fill the other nucleus, so there will be attraction. And this nucleus will also fill the other electron, there will be attraction. This is dipole-dipole interaction, that is attractive. We did not discuss this electron to repulsion when they're very close, because Leonard-Jones is how? It goes sharp, it decays like this, and then it goes below, and then it comes to zero from below. When it goes below, that is the attractive part, and that comes
Yes, sir.
this part is the attractive part, and that comes from what? R to the power 6, 1 by R to the power 6 minus, and this one is 1 by R to the power 12. So if you add them, they will go like this. Both are quantum mechanical origin, but here I talked about the van der Waals interaction at a length scale which is not very close. Since I did not do the derivation, if you do the derivation, you will see how it comes. If you want, I can send you a note on this. If people are interested, I can send a note on this, or I can set an assignment problem on this. Maybe I'll set an assignment problem on this. So how many of you are doing the assignments? Assignment is due on 19th of October before midnight. So you have like 11 days left. Okay?
Yes, sir, we are trying.
You're trying. So Ion, you are in MSc.
Yes, sir, I mean, yes.
Okay. What about
Sir,
others? Yeah, Tishan, tell me.
sir, I was just curious, like uh, in the variation method, like we will have to guess like wave function for every energy state, like for ground state, first excited state, and for every state we will have to guess a
No,
different
I
wave
did
function.
not discuss. I did not tell you that this is this is only for the ground state. Variation
What about
principle, yes.
other state, like
Yeah,
wave?
because in chemistry, many times we are interested only in the ground state.
Okay.
If you're doing spectroscopy, you're interested in the excited state, but that is the problem in the quantum chemistry. Problem means very challenging. Because of that, you know that we don't have good wave function for the excited states. So the calculation, excited state calculations are challenging. For example, in ground state, even ground state we don't know, that we can guess using variation principle. So but there is no variation principle for the excited state, because whatever energy you calculate, that will be higher than the ground state. It does not tell you anything about the excited state, isn't it? So
And
you are
sir,
interested to know what is the ground state energy, closest best approximation to the ground state energy. Yes.
Okay. And sir, like in this course further, like we are going to learn about the valence bond approach, like that was done by Linus and Pauling. Like for the hydrogen atom, they were just flipping the electrons and all that. Like that is what we are going to study about, right?
Yes, I want to teach that. Hopefully, I'll have time. But this course is quite. It has a lot of things actually, quite heavy, I'd say. No, like it has the components of quantum mechanics. Then you have quantum chemistry and all these things. You have to cover many topics. For example, I could not do what is known as Stark effect. You know Stark effect or Zeeman
Yes, I've
effect.
heard.
You guys
Yeah,
know
Stark
about it.
effect and Zeeman effect.
Yeah.
Yeah,
So
splitting
the
of p orbitals.
Stark effect is application of the electric field externally and then perturbation on molecules. And the Zeeman effect is same thing, not same thing, but for the magnetic field. When you apply magnetic field, then what happens? These things are very important, but I could not do. Maybe I'll try to set question on this in the assignment. Because if I do this, then I'll not be able to do anything on other things. I don't have time. This course has too many things, and it is also clubbed with 812. 812 syllabus is slightly different, so I have to touch on few topics which are included in 812. So I would suggest to please go through this. This is the book, Molecular Quantum Mechanics. I have the 3rd edition, that is good enough. It's a very nice book. How many of you knew about this book? Atkins, this book, not the physical chemistry book. This is a very nice book actually. You can just try to get it. It will be quite useful for chemistry students. Okay, with that I'll stop presenting and stop recording as well.